Moving on to 18. Give an estimate for e to the 0.1, which is accurate to 3 decimal places. So this one is not immediately obvious what to do. But the magic, this is where these Taylor series are actually useful, is I know e to the x, this is number 18. I might have said 17, this is 18. I know e to the x is sum n equals 0 to infinity x to the n over n factorial. So therefore, e to the 0.1 would be sum equals n equals 0 to infinity 0.1 to the n over n factorial. So now I need to guarantee that it's within 0.1. So how can I do that? We can use Taylor's inequality. So I don't necessarily know how big e to the 0.1 is. I know it's bigger than 1, but I really don't know what it is. But I know on 0 to 1, so some small interval there, 1 is less than or equal to e is less than or equal to 3, e to the x. Because even if I plugged in 1, I would get e, which is like 2.718. But I'm going to use this number here, this 3, in this, because what do I need to do? Taylor's inequality says my nth remainder is less than or equal to m times x minus a to the n over n factorial, but this is a plus 1. No, that's not right. The plus 1 comes on the m. But what is this m? Where f to the n of x is less than or equal to m, at least on the interval. So here we can use m equals 3. So we can use m equals 3 by what we said here. That's as big as e to the x even gets. And e is its own derivative. That's important. As f to the n of x equals e to the x, which is less than or equal to 3, again, on 0 to 1. So we're using that e is its own derivative here, but that's what we get. And a is 0. Did I write that yet? No. A is 0 because that's where this Taylor series is naturally centered. So we need Rn to be less than or equal to, we want it to be within 3 decimal places. So for safety, we go out one more. We need this to be less than 0.0001, because then we'll really get a good idea of what it's supposed to be. And so I need 3 times 0.1 to the n over n factorial. We need this to be less than or equal to 0.0001, because then by Taylor's inequality we'll be good. And so we would just keep plugging in values until we get what we need. So if we look, the least n where this works is n equals 4. So we use S4. So we plug in the first 5 terms because there's a 0 term there. So we use sum n equals 0 to 4 of x to the n over n factorial. We're going to plug 0.1 into this. So this is x to the 0 over 0 factorial. We haven't plugged in yet. X to the 1 over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial So plugging in 0.1, we get 0.1 plus 0.1 over 1 plus 0.01 over 1 plus 0.001 over 1 plus 0.0001. Sorry, these aren't 1. 2, 6, autopiloted there. 24, plug those in. 0.1 plus 0.1 plus 0.01 plus divided by 2 plus 0.0001 divided by 6, 0001. Divide that by 24, and I get 0.2051. So I should comfortably be able to do 0.05. Let me just check what e to the 0.1 actually is. What did I mess up? Oh, this shouldn't be a 0.1. This should be a 1. And if I do that, I would get 1.105. 1 or 2. So I round this and I get 1.051. And when I compare that to the actual answer, that is just about right. Definitely good to 3 decimal places. But we guaranteed that would happen. That's not luck. We made that happen through Taylor's inequality. So that's why that works. All right, and that's number 18.